Alright, so I'm going to be doing problem 27 from the book, chapter 14, subsection 3. It's a problem where we're going to be converting from Cartesian coordinates to polar coordinates. Here's the two iterated integrals that we're going to be evaluating eventually once we convert to polar coordinates. So with a problem like this, I usually like to start off by drawing the space that we're going to be looking at. So here's one region that we've got. The boundaries for this are 0 to x in terms of y. So you've got y equals x and you've got y equals 0. And then you've got your boundaries for x. You've got 0 and 2. So that gives us a nice little triangle. Pretty simple. Then the second region that we're going to have is going to give us this. So all we're doing is adding this second region right here to the triangle that we already had. The relevant portion of this is going to be right here, this purple section. So our boundaries for y are again going to be 0, so same there, and then it's going to be this arc here, this semicircle, this quarter circle, and that's bound by this function right here. So root 8 minus x squared. That's what kind of shows us that we're going to have a situation where polar coordinates are going to be the most useful, because we are evaluating this little slice of a circle, basically. And then our binds for x continue at 2, and then they go to 2 root 2, which works right here. That's kind of relevant, since that point does meet. We're going to be using that again in the next step. So now that we have this picture, we can go ahead and take these two iterated integrals and put them into one iterated integral. And that gives us this right here. So all we're doing is taking the boundaries of this region in terms of polar coordinates. We have a radius of 2 root 2, and we have an angle of 0 through pi divided by 4. So that looks like this, basically. Alright. So, again, 0 to pi over 4. It's going to be our value for theta, right here. And then 0 through 2 root 2 is going to be our radius. We don't have a chunk out of the center or anything, so it's pretty standard, 0 through 2 root 2. Then the only thing that's left is to convert the function that we're actually integrating over, and that's going to be root r squared times r, which we're going to simplify a little bit in a second. But it's nice to see it in this form because it makes it really easy to see what we're taking out of this to get that. And that's we take the fact that we know x squared plus y squared is r squared, and that's because, you know, when you have r cosine theta and r sine theta added together, your the cosine and sine are going to cancel out, so you're just left with r squared. So once we have the r squared, the root here, we've got to remember, since we are converting to polar coordinates, it's important to bring this extra r in here, which in a lot of the situations I've seen where you want to convert to polar coordinates is really useful. It's going to be really useful in this situation as well. It's a lot easier to evaluate. Well, actually in this one it's not. But if we had like 8 plus r squared or something like that, it's going to be a lot easier to evaluate that with this r outside of the root than it is going to be without that. So it's kind of nice, really, that it does add that in there. So we can simplify this down a little bit, and when we do that we get this. So this is what we're really going to be dealing with, not the other one, which again is why it doesn't really matter that we did have that extra r in this particular circumstance, since the root did simplify out. So from here on out it's pretty simple, really. We start off by evaluating in terms of r, and we get this right here, and then we iterated over this range, and we get this right here. So we just sub in these values. We get straightforward numbers. Nothing tricky about this. Then we want to integrate in terms of theta. So we're going to get this. Again, very straightforward. We've just got a constant that we're integrating. And then we evaluate that, and we get our answer. So here's our answer right here. I went over the last couple steps kind of quickly, but most of this stuff should be pretty straightforward to everybody. It's this part that's really the interesting part. So taking this to this. We really haven't seen many of these problems where it's a sum, but once you draw it out, it's almost exactly the same as any of the other ones that you're going to be encountering. So I hope this was helpful, and that's the problem.